Hey there, we're going to review over some work and power information and then work some practice problems together. And so far what we've learned the definition of work, and we said that work was equal to that parallel force times the distance that it travels. And then we also seen where work is equal to a change in energy. Okay, we've seen this between both the lab activities that we've done over the last few days. And we're going to kind of summarize here in this table kind of what's happening. So work is positive, and in terms of forces, that's the case whenever the force is in the direction of motion. So it's in the same direction as a motion. And in terms of energy, work is positive when the energy increases. Work is negative in terms of forces when the force is in the opposite direction of motion. And in terms of energy, work is negative when the energy decreases. And work is zero when the force is perpendicular to the motion. And in terms of energy, work is zero whenever the energy doesn't change. So that's how we know when work is positive, negative, or zero in terms of both forces and energy, because we have two different ways that we can solve for work. One in terms of forces and one in terms of energy. So we're going to work a couple problems here. The first one says that a car has a mass of 150 kilograms. It's moving at 10 meters per second. How much work is needed to speed it up to 30 meters per second over a course of 40 meters? And what's the average force on the car? So our first equation that we learned, we had work is equal to the parallel force times the distance. But in this problem, I don't have the force information. I do have the distance, but I don't have the information about the force. So I can't use this equation here. That means that we're going to have to use an equation in terms of work is equal to a change in energy. Now, in our inclined lab, our change in energy was a gravitational potential energy. But in here, in this problem, it's not gravitational uh, potential energy, it's kinetic energy because it's dealing with the motion of the car. So for this problem here, work is going to equal to your change in energy, and specifically it's going to be a change in kinetic energy. And remember, whenever we have a change in anything, it's going to be the final minus the initial. So it's going to be your final kinetic energy minus your initial kinetic energy. So for your kinetic energy, remember it's equal to 1/2 mv squared. So we're going to do that both for the final and initial kinetic energy. So work is equal to, we have 1/2 the mass of the car, which is 150 kilograms, times the final velocity of the car, which is 30 meters per second, and that's squared, minus the initial kinetic energy. So you got 1/2 the mass of the cart, still 150 kilograms, times the initial velocity of the cart, which is 10 meters per second, and then that's going to be squared. So when I punch that in, I should end up with 67,500 joules minus 7,500 joules. So the work here in this case is equal to 60,000 joules. And the second part of this problem, it asked me to find what the average force is. Now we can go to this equation here to solve for it, because now we know work and we know the distance was 40 meters, so we can solve for that average force. So write our equation out, solve for the force, and now we can plug in. And when you punch that in, you should get 1500, and it's force, so it's newtons. So that's whenever we have a constant force, and using that equation, work is equal to force times distance. Excuse me. Sometimes, though, we don't have a constant force. Okay, sometimes we have a variable force, and we'll get into that one here in just a minute. Before we do that, let's kind of look whenever we have a force exerted from an angle. So for this problem here, it shows us a free body diagram. The object moves 4 meters to the right, and we're going to calculate the work done by each force and then the net work done on this object. So looking at that, we can first find the ones that have zero work being done, and those are the ones that are perpendicular to the motion. Because remember, back up here on our chart, we have a zero work being done if it's perpendicular to the motion. So we have two forces here that are perpendicular. Since it's moving to the right, any force in the vertical direction is going to have a work of 0. So that's going to be my normal force, and it's going to be the weight. And both of those are 0 because they're perpendicular to the motion. Now we can look at the other forces. Let's start with the friction, okay? Because the friction is only in the x direction. So the entire friction force is going to do work on this object. So for your friction, work caused by friction, it's going to be the force of friction times the distance. And your friction force here is 40 newtons, and the distance was 4 meters. Now it's to the left and it's moving to the right, so that's going to be negative 160 joules. And remember, back at our table, if it's in the opposite direction, it's going to be negative. So the last one we have is tension. Now remember, it's only the parallel component. So not all of my tension here is going to be doing work. This part, the y component, that's going to be perpendicular to the direction, so it's not going to be doing work on this object. So we need to find our x component of tension, because that's the one that's doing work. So here's your angle. You know the hypotenuse there. We're looking for the adjacent side, so we're going to use the cosine function. So cosine of 60 is going to equal your x part divided by 70 newtons. So the x component is going to equal 70 newtons cosine 60. And to find the work from this x component, we just got to multiply it by the time. So it's going to be that tx times the distance, 70 newtons times cosine 60, times your distance of 4 meters. And when I plug that in, you should end up with 140 joules. The net work, then, we just add all that up. So you should end up with negative 20 joules. So that's how we can find the work caused by different forces. Now let's jump back into one of those examples where we had that variable force. So when you have a variable force, in other words, it's changing, okay, that's what that means, is that it's not a constant force. We're going to find the area under a force position graph. So here's a force position graph, and we're trying to find the work done. Remember, work is equal to that parallel force times the distance. And when I find the area underneath the curve here, I can break it up into my shapes. I'm going to take my y-axis and multiply it by my x-axis. That's force times that distance. So that's work. So let's break up our shapes. Should end up with this. We have two triangles and we got a rectangle. So this one, the area here, is going to be the length times the width. So we got negative 40 times 2. For this triangle, 1/2 your base times your height. And for this triangle here, we got 1/2 your base times your height. And so the work then is going to be all of these areas added up. So you got negative 40 times 2 plus 1/2 negative 40 times 2 plus 1/2 40 times 2. So when I start solving for all these, we get negative 80 joules plus we have a negative 40 joules plus we got a positive 40 joules. So these two will cancel out, and the work done here is just negative 80 joules. So again, whenever we have a variable force, we're going to be given this force position graph, and we just find the area underneath the curve. So to kind of sum up, there's two examples when the force on the object, or when there is a force on the object, but there's no work being done. Okay, those two scenarios are when the force is perpendicular and when the object doesn't move. So in these two situations, there is a force, but there's no work. All right, so that kind of goes over and reviews work. The last little thing here that we'll talk about is power. And we'll kind of review that. So we did a power lab. We ran the stairs. And for power, it's really the definition. If I look at the definition of power, it's the rate at which work is done. And if I put that in an equation form, your power is equal to your work divided by your time. Now on the power stairs lab, it was written as work was equal to your change in energy over time. Remember, work is equal to change in energy. So either one of these formulas are correct. Both of them are the same thing. It just depends on the information we're given. If we're given information in terms of forces and the distance, then I can solve for work using that parallel force times distance. Then I can plug that in and solve for the time. So I could kind of further break this down and say that power is equal to the parallel force times the distance divided by the time. And then I can also do it in terms of change in energy. Okay, we've seen the power or the work on inclined plane lab where we had a change in energy was gravitational energy. So in that case, it'd be your change in gravitational energy divided by the time would equal your power. And the practice problem that we had with the car earlier, our change in energy was kinetic energy. So in that scenario, your power or your change in energy was kinetic energy. If I divide by the time, then that's how I would solve for power. So it really just depends on what's given in the problem. But there's two ways to solve for power in terms of one in terms of work, one in terms of energy.